So, sure. So up until now, we've only done the integration using, well, equal step lengths. So say you have this function here. Cool. Okay, so it's called equidistant nodes. Then we have this function here. Okay, f of x here. So equidistant nodes, that means that they are equally distant. It's kind of in the name. But using equidistant nodes here is not, well, it works, but it's inefficient. What you could do better is, so you see this area, there's a lot of variations. So actually, slicing this area into smaller pieces, and then this piece here, you could actually do the whole thing in one go. And then here it's less variations. So we can use larger slices. So the point here is now to figure out how can we dynamically scale the grid spacing. We'll do some nesting and recursions. So doing this more efficient, more accurate, and the way we'll do it here, we also get an error estimate out of the solution. And I can also mention that it's used in most commercial software to have some kind of adaptive quadrature. So hopefully I'll have time to show my implementation of this and then compare it with MATLAB's. Of course, MATLAB is better, but it's a step. Again, we want to integrate from A to B f of x dx some kind of integral I, some kind of value. And we want to do this with some kind of specific tolerance, epsilon. Tolerance. So, how can we do this? Well, we can apply Simpson's rule. Say h again is b minus a divided by 2. That means we are using the whole domain. So for this, we'll get dx equals Simpsons h. So h here is going to be the full domain. And then of course, error 590. Value 1. Between A and B. Also, if you want to compare this with yesterday's lecture, I think I wrote 4. This is same. Rewritten the h's, so it's still h4. So it's still the same we had yesterday. This case, s of h going to be h over 3 a for f row. Oh, this is in psi. Oh, okay, yeah. Because yesterday I used zeta. This, you mean? There's no reason. There's no difference. I mean, it's just placeholders. If you want, you can call this an apple and appear in banana. It's no, it's but it doesn't really matter. So let's roll. Let's sigh. What's the difference? Maybe not in the blackboard, but yeah, this one has a shorter loop data, but it doesn't really matter. It's just a variable placeholder. So I mean, it's the same. Why f? Well, it's a function. Why a and b? Well, it's the first letters of the alphabet. Why this? Well, it's an s because it's a sum. It's also this. So this is a digression though. This is also a sum because it's an s. So it's just, well, yeah. I've actually asked some colleagues of mine who are Russian, why don't they use Cyrillic letters? They don't know. Oh, weird. I mean, if you want to deliver your project using smileys as variable names, you're welcome. You have to figure out how to use smileys in LaTeX though, but well, I'll use Word. So. Anyway, I guess I can reuse this. Well, actually, I'm curious if you get emojis in LaTeX, that would be interesting. Then I want to see how you solve it. Okay, so I'm just going to reuse this graph. So we're going to say that the function we are integrating right now is something like this. And right now, since h is b minus, no, since h is ba, b minus a over 2, that means we have kind of one interval. So here, else it will be. Okay, so now we only have one interval or two subintervals. It depends on how you want to count it. So a over here, h, and b. Or also this length here is going to be h. Okay. So this is one way of doing it. The problem here is we don't really know the error we have at all, so we have to figure out some kind of other way of calculating the error. So these guys. Okay, so what we do then is we try to use a Simpson, but with a different h. So we are basically splitting this into two again. More colors. Now we want to estimate this interval here. Okay, so basically we're splitting into smaller parts, but we're keeping the same h. So we have to be careful not to do. So, do this. Now we say that also basically it's the same business rule, but we say that if you remember back, this m is the amount of subintervals here. So before we only had one, now we have two or four subintervals. We'll probably use that up as well. Okay, so for this new one, we will have, we'll call it h half. Six a plus 4 f a plus h half 2 f a h, and then I'll continue down here. Or f plus h 2 plus b. And then the error for this one is going to be h2 or a 90. It's 2 now. And f4. So we will stick with I. So, but this is a different one. But the thing is, we don't really know this value or this value, but we can assume that they are kind of the same. But what we've done here, basically, we're splitting it into two. So have this one over there. Go to say I do this. Okay, so I'm going to use this instead of a simple parenthesis to indicate which interval it's over. This is going to be over from a plus 2. So that's the first one. H6 a plus all to I'll try to illustrate again. Starts H middle one or F H2 plus F of like so. Okay, so this is basically the idea over here again. So in, I'm not sure if it's visible back there, but so in brown, that's the function and the first estimate. So the estimate over here using these 3 points, that's the one in white with the lines going this way. So that's one estimate of the integral. What I've done all the way over to the right there, that's the yellow one. So then I have more subintervals. I still have this error. So basically, I'm also saying that integral is equal to this, but it's also equal these two. So S A I just call it H, because this is this. 2 plus B minus 1 over 16 590 F of this here. Okay, so the blackboard is a bit noisy right now. I'll try to circle. So what we are actually after now is this equation and this one over here. So those are two estimates of the integral. The problem we have though is this and this. We don't really know what they are. What we can do an assumption, and we can say that they are somewhat similar. Did I make too much of a mess on the blackboard, or are you still following me? You're nodding. Okay, so what we're going to do, we are going to assume that this one is almost the same as this one. Which means that this one is approximate this one. So that's an assumption we can do. If it actually holds water, we don't know, but it's an assumption we do. We just say that there's some kind of error in there. Okay, so we're assuming this, and we get that. Comparing the two equations I've circled, we'll have that S of A plus B O 2 A plus B O 2 B as 16. Oh, 1 over 16. 16. 5. 9. 4 there. Approximately equal to full interval five. Okay. Basically, what it says is that splitting it up in two intervals will have, well, this error approximately the same as this error, but only less. (1/16) less. So this will give us that the difference from the integral, so f of x x minus a plus b over b over 2b approximately 1/10 of Simpson's method on the whole interval minus b this. B over b2 like so. Okay, so what does this tell us? So this is basically, maybe it's more clear if I put a parentheses. This plus there, since it's minus. So basically what this says is that this thing, so splitting it into two integrals, is approximately 15 times more accurate than estimating the integral over just one interval. Which is kind of the key point here. This we can use. Okay. So I'm going to reiterate. The distance between the true value of the integral and this approximation is about 15 times smaller than the distance between this way of approximating the integral, just one interval, and approximating with two intervals. Okay? Make sense? Okay, write that up. So, conclusion. If distance a b a b over 2 a plus b, if then of this error, then know that b x minus a o2 should have had some shorthand notation for this, but too late. Less than epsilon. And the whole goal here is that we want to make sure that, oops, that, yeah, I mean, this is basically what we want to show. So we want to have an estimate that if you know that the difference in this way of of doing it and this way of doing it is less than 15 times the error tolerance you have, then you know, assuming that this holds, why shouldn't it? Then this one is less than this epsilon. That is a good approximation. Okay, so the good thing here is that we have just discarded these. We don't really need these. Again, assuming this. And then this one, we've already calculated it. And these two we can calculate. And if it works, the better one. So I'll try to show an example of this of time. Can I take this off? The left side? Okay, we'll try to look at by half dx. We know that this is 1. I hope that's true. Okay, so if we try to do the Simpson's method on the interval from 0 to pi half, we will get approximately 1.0022 given. So that's we just 1. Okay, what happens if you try to do it with 2? So from 0 to pi fourth, pi fourth, pi half. Zero, 0, 1, 4, 6. Do I have a... Oh, no. Okay, so this is better, but let's take a look at the different values here. So we see that I need more. I don't remember what I just... Okay, so that looks at 1/15. Yes. Can I say that this is S, let's call it F for full, and this is a B, just for shorthand notation. At the full interval, oh, it's just, I made it up on the fly. So this is just the full interval. This is the A part of the interval. Yeah, let me do this. This is A and B. Okay? I'm just making a system in my head here right now. I'm saying that, say, pi half. I'm saying that this region of the graph A and this region of the graph is B. Yes, tell this AB. So SAE. This is just to save some chalk and a lot of writing, because you don't need to repeat this. You know what it is. Minus of A plus. Okay, then I hope the equations are correct. Supposed to be 0.04 integral of x 0 pi dx minus SA plus B. Well, that's 0.0001. So we see that kind of works. This is 1/15 of it. So we see that if actually this holds, it's less than some number, this is, so it's 15 here. I could also have done times 15. This. Could be that the calculations are off, but I hope they're correct. Yep. Yes, it's from the earlier notes. So you saw I had, yeah, 1/16. But you also have this other part of it over there. So then you would have, I don't have the notes anymore like this, but you have 1/16 on one side, and then on the other side, this will cancel and be 1/15. Could be I have to do this again, but I'm pretty sure it's going to be 1/15. Yeah, yeah. Mm. Yeah. Yes. It should be correct. It was correct when I did it earlier, at least. um. Oh, it's valid. Um. I would say these numbers are pretty equal, because I have the 15th over here. So these are the same order of magnitude, at least. But they both start with, well, 0, 0, 0, 0, 0, 1, 1. Yeah. That is basically, so this is all approximations. But it's just to show that it does kind of work, even though sign is varying on this interval a lot. 0 to 1. Notes here. Okay, so what you want to do is, you want to always try to, so you're given an error, an epsilon. What you want to do is, you want to always divide it down, and then you see if then you try to calculate this sum, and then you see if this is less than 15 times your tolerance, then you accept this level. Then you accept this level of partition of your graph. And then you're happy. Then you don't have to go any further down. So quickly before the break, what you have your full interval here. Okay? And then you try to split it. Split it in more space. This is your interval. Okay, first, split it in two. You would have this interval here, this interval, and then you can compare the approximation of the integral on this interval and on these two, and then you see if this sum here is less than 15 times your tolerance, then you accept this level. But it could be that you need to go deeper, so you maybe have to split this again. Oop. Maybe you have to split this again. So you're always checking and checking and checking. So I'm not sure if you've used to recursive relations, but you have kind of one function that works up here, and you see you can apply the same down here. You can just call the same function over and over again. And I think we'll do that after the break. We'll actually do the algorithm of it, try to explain it in detail. Yes. So 15-minute break.